black hole. Two simple words that together describe one of the most extreme and mysterious objects in the entire universe, something so strange that even over a century after Albert Einstein's equations first hinted at their existence, we are still far from fully understanding what lies inside. A black hole is not, despite its name, an empty hole in space, but rather a region where matter has collapsed to such a high density that gravity completely dominates over all other forces of nature, curving space and time to the point where nothing, not even light, can escape its pull. That is why, from the outside, it appears perfectly black. To understand what a black hole is, we need to go back to the general theory of relativity, published by Einstein in 1915. This theory describes gravity not as an invisible force acting at a distance, as Newton imagined, but as the warping of the four-dimensional fabric of space-time by mass and energy. When enough mass is concentrated in a small enough region, space-time can become so curved that it forms a one-way boundary, what we call the event horizon. This is the point of no return. Once you cross it, no possible path will ever lead you back out into the universe. Most black holes we know about form as the final stage in the life of very massive stars. When a star with at least about 20 to 25 times the mass of our Sun runs out of nuclear fuel, it can no longer produce the outward pressure needed to counteract gravity. In smaller stars, electron or neutron degeneracy pressure halts the collapse, leaving behind a white dwarf or a neutron star. But in the most massive stars, gravity overwhelms every known form of pressure, collapsing the core beyond any known limit until it shrinks to a point of nearly zero volume and almost infinite density, a singularity. The singularity is where our current understanding of physics breaks down. General relativity predicts it, but quantum mechanics, which governs the smallest scales, cannot yet be combined with relativity into a single theory of quantum gravity. Black holes are therefore natural laboratories for testing the very edges of human knowledge, places where the most successful scientific theories ever created run into contradictions. Surrounding the singularity is the event horizon, a spherical surface whose size is set by the Schwarzschild radius. For a black hole with the mass of our Sun, this radius is only about 3 kilometers, or less than 2 miles, across. For a supermassive black hole at the center of a galaxy, it can be millions of kilometers wide. Whatever crosses this boundary, whether it's a particle of light or an entire planetary system, is lost to the outside universe forever. Because nothing can escape, we cannot directly see a black hole itself. Instead, we observe its effects. Material spiraling and forms an accretion disk, where gas and dust heat up to millions of degrees, emitting intense X-rays and even gamma rays. Astronomers also watch stars orbiting something invisible but extremely massive, revealing the black hole's presence. This is how we confirm the supermassive black hole in the center of the Milky Way, known as Sagittarius A. And in 2019, the Event Horizon Telescope gave us our first ever image of a black hole's shadow, the bright ring of superheated gas around the supermassive black hole in galaxy M87. Not all black holes are the same. There are stellar mass black holes formed from collapsing stars, supermassive black holes in galactic centers containing millions or billions of solar masses, and a few candidates for intermediate mass black holes that may form through the merging of smaller ones. There's also the intriguing idea of primordial black holes, hypothetical objects formed in the extreme conditions of the early universe shortly after the Big Bang, which could be tiny or massive, and might even account for some or all of the universe's dark matter. Black holes aren't completely black. In the 1970s, Stephen Hawking showed that on the quantum level, black holes can slowly lose mass through what's now called Hawking radiation. For large black holes, this process is unimaginably slow. A black hole with the mass of the Sun would take far, far longer than the current age of the universe to evaporate. But for small black holes, the effect would be more significant. And what would happen if you got too close? Long before you reach the singularity, you'd experience extreme tidal forces. The difference in gravitational pull between your feet and your head would stretch you into a long, thin shape, a process scientists vividly call spaghettification. From the point of view of someone watching from a safe distance, You would appear to slow down more and more as you approach the event horizon, with your light shifting to redder wavelengths until you seemed frozen at the edge. But in your own frame of reference, you would cross the horizon in a finite amount of time and fall toward the singularity with no chance of escape. Black holes captivate scientists and the public alike because they represent the ultimate test of our theories and perhaps the key to understanding the deepest structure of reality. Some speculative models even suggest that a singularity could be a gateway to another universe, or that the interior could be connected to a distant point in our own universe through a wormhole. While such ideas remain unproven, they show how black holes inspire both science and science fiction in equal measure. Whether we think of them as cosmic destroyers or as vital players in shaping galaxies and influencing star formation, black holes remind us that the universe is far stranger and more complex than we can easily imagine, and that every answer we find only leads to deeper, more challenging questions. Subscribe us for more videos.